Let's start. Today we are going to talk about min-max optimization problems. You have already seen various applications and various formulations that min-max optimization problems appear. For example, we saw some examples of min-max in adversarial learning when we were doing adversarial training to robustify models. Last lecture, you saw one example of min-max in training generative models like GANs. And there are many other examples that min-max optimization problems become relevant, for example, in multi-agent reinforcement learning, among many other problems. Okay. All right, so today I'm going to cover basic results, classical results in the min-max optimization, and then I'll talk also about very recent results in this area. So in part of today's lecture, I'm going to use some materials from my good friend's talks, Kostas Kalakis, and I think he has very interesting papers and results in this area, and some talks also on YouTube that you can, take a look to get a more theoretical view to these problems from a computational complexity point of view, specifically. Okay, let's start. So, what is the problem that we are going to consider today? We have a minimization over x variables belonging to, let's say, a set cal x, and we have a maximization on y variables. And our objective function is in the form of fxy. Okay, so this is called a zero-sum game. So why it is zero-sum? Because you can think about both players maximizing an objective, player y maximizing f, and player x maximizing minus f. So the reward for these players will be sum to 0. So that's why it is called zero-sum game. And in general, x and y can live in a high-dimensional space. So one assumption that I'm going to make throughout today's lecture is that f is smooth and continuously differentiable. So f is a nice function. Not sure if it is convex concave at this point, but we are going to make this general assumption. All right, so what is the goal of my optimization? So my goal is to find a global solution, or sometimes called global saddle point or global equilibrium for this min-max optimization or game. Right? So I want to find, let's say, x star, y star. It is called global solution or a global saddle point or a global equilibrium. Okay, so what are the properties of this global solution that I want to have? Y star, I want the player the y player, the max player, the y star that it has, it should be optimal for all other values with respect to all other values of y if I plug in x star in my objective function. So this y star is the arc max of my objective function if I plug in x star. So if my x player uses x star as its value, so this function will be a function of y, this y star is the best. So the player, the max player, does not have any incentive to change the value y star to another value. And same for x star. So if I fix my y to be y star in my objective function, so this objective becomes a function of x, and x star is the minimizer of this objective function. So there's no incentive for the mean player to change the value from x star to another thing. So another way to write these two equations in one formula would be, let's say I have x star and y star. So this should be less or equal to f xy star. So if I fix y star, this x star is the minimizer of this objective function. So f x star y star is less or equal to f x and y star, and vice versa. So if I fix my x to be x star, y star is the maximizer. So I have the other side of the inequality for all x and y in, let's say, my feasible set. Let's say S contains all pairs of x and y's that are feasible for my optimization problem. All right, so that's the goal. That's the the purpose of solving this optimization, to see if we can find these global saddle points or equilibriums or solutions. Okay. So the question is how we can solve this optimization, right? That's the, because we are in some level in practice, we get like these optimizations, min max and adversarial robustness in GANs. And at the end of the day, we wanna solve these optimizations efficiently and see if in fact those solutions are global solutions for that optimization. Right, so how to solve? How to compute x star y star? Right, so you have already seen some solvers for this min max optimization problem. Can you recall? So in GANs or in adversarial robustness, how do we solve this min max optimization problem?
Alternating gradient descent.
Yes, yes. So that's basically a first order method to solve a min max optimization problem. Right? So a common approach is, let's say, via first order methods. Right? So a popular first order method that we have already seen is something called alternating gradient descent ascent, or a slightly simplified version of it is called simultaneous gradient descent ascent. Or GDA. All right, so here we are going to take one gradient step to optimize both x and y at the same time. So what are my updates? I have, let's say, x at time t plus 1 would be the same as x at time t. I'm minimizing, so I'm going to go in the negative direction of the gradient, minus eta times gradient of my function evaluated at point computed in time t. And similarly, my y at t plus 1 would be y at t plus y plus, because we are maximizing. Eta gradient of my objective function evaluated at time t. So this is called simultaneous because if you notice in the updates here, so both of the updates depend on values that we computed in the previous iteration. So a slightly modified version of this is called alternating gradient descent. Then you update X and then use your updated values in updating Y and vice versa. So they're quite related to each other. But for the purpose of today's lecture, we are going to focus on simultaneous gradient descent. Okay, so one note here is, so these updates are in the unconstrained case, right? So your cal X and cal Y, your feasible set are, let's say, in the entire d-dimensional spaces. Let's say cal X and cal Y are in fact RD. If you are in a constrained min-max optimization problem, you got a project. After these updates, you got a project back to your feasible set. In the constrained case, after each update, we need to project back onto our feasible set S. Okay. Let me pause and see if there are questions. I see some questions in the chat box. Is there any order to update X and Y? Good question. So far, no, right? It's simultaneous. So we update both of them at the same time. If you look at alternating gradient descent, you may start with one player and update the other player. So there's another related question asking if this analysis holds for max min 2. So I'll talk about that in a minute. So we'll see if we can, in fact, switch between max and min in the objective function. Okay, so let me move on. All right, so to simplify this notation, let me introduce theta that includes both X and Y variables. So I define theta that has my mean variables and my max variables, both of them. So in that case, I can write the dynamics of GDA, simultaneous GDA, as one update equation on theta. So in that case, I'll have theta at t plus 1, which would be basically these two terms, would be equal to theta times t plus eta, which is my learning rate, times the gradient vector. So this is the gradient vector evaluated at theta t. So what is this gradient vector from these equations? So this gradient vector, all right, so note that here I put the positive sign, but here I have a negative sign. So the one component of this gradient would be minus gradient of f with respect to x, and the other component would be plus gradient of f with respect to y. So I'll have minus gradient of f with respect to x, and the other one would be plus gradient of f with respect to y. Just rewriting the dynamics of GDA in one equation. So it makes things a little bit simpler. So I can even further simplify this, because this is a function, this whole right-hand side. Let's say it's a function applied on theta t and gives me theta t plus 1. Right? So this function is basically theta t plus eta times this gradient vector. Right? So I have this function defined, applied on theta t gives me theta t plus 1. Okay, so here I start with, let's say, theta 0. That's my initialization for x and y. So this function f I compute at theta 0, then it gives me theta 1, which is f of theta 0. And then I apply this function again on theta 1, and I compute f theta 1, which is theta 2. Right? And then I keep doing this. So when I can claim I will converge to a solution. Let's say I converge, I have like this theta star. So remember, in the global saddle point, I don't have any incentive to update my parameters, right? Because of these equations that we have here. If you are in a theta star, then you don't have any incentive to optimize your, to update your parameters. So if I'm ending up in a theta star here, and if I apply this update f, then I like to remain at the same point, right? So I don't want to change my parameters. So if I apply f to this, I should end up in the same point theta star. So in that case, this is called theta star would be the same as f theta star. So here, theta star would be a fixed point. A fixed point of f. So I apply f multiple times. At some point, if I'm stuck in somewhere, if I apply f, I don't go anywhere, it means I have converged. So there is no other point to go, because if I apply f one more time, I'm gonna remain in the same point theta star. So that's why it is called a fixed point. Okay. So I'll talk about the conditions for the convergence and also the optimality in a minute. We may not actually converge, right? So there I may have an f that never converges to a point theta star. So that's something that we'll talk. So actually, let's look at one example to make it a little bit more clear. Let me consider perhaps the simplest objective function for my min-max. I have min over x, I have max over y, and let's say my function is just x times y. And for simplicity, let's consider these x and y to live in reals. One-dimensional variable, really simple. Okay, so let's write the dynamics of GDA. Let's see if it will converge to my global saddle point. So global saddle point for this optimization, it is really easy to check that it is just the origin. My global saddle point is just 0, 0 here. Because if your x is 0, then your objective becomes 0. There is no, your y won't, need to change, and vice versa. So that's the global saddle point for this optimization. Okay, so let's write the GDA dynamics. So in order to do that, I need to compute the gradient of my objective function with respect to x and y. So what is the gradient of this function with respect to x? It's just y. What is the gradient of my objective with respect to y? It is just x. Right? Very simple. Good. Now, if I want to write the dynamics, my xt plus 1 would become xt minus eta times gradient of my objective with respect to x, which is y. And my yt plus 1 would become yt plus, because I'm maximizing over y, eta times gradient with respect to y, which is just x. Okay, in fact, you can write this as a matrix. You can say xt plus 1, yt plus 1 is, okay, so let's see. So you have xt, yt here, so minus eta, eta 1. So you use this matrix in order to update your xt, yt to xt plus 1, yt plus 1. Right? So question, in this case, does GDA converge? Say if I continuously apply this update, would I converge to a particular point? Specifically, I want to see if I would converge to my global saddle point.
Is the step size fixed?
Yeah, let's say it is like 0.1. Or let's say it is like very small, whatever you like, but it's positive, right? So eta is positive. Okay, so I see like mixed responses in the chat box. Some people say yes, some people say no. Good. So let's build some intuition first about these updates. All right, so let's say this is my x-axis, this is my y-axis, and let's say I am at a point 1, 1. Right, so that's my xt, yt. So xt plus 1 would be 1 minus eta, right? Because of this update. And yt plus 1 would be 1 minus eta, would be 1 plus eta because of this update. So I'm gonna go in this direction. You know, similarly, if you look at, let's say a point minus 1 and 1, you can see that you're going to go in this direction. And here you're going in this direction, and here you're going in this direction. The question now is that it's like kind of, you know, in a circular fashion. The question is that are these flows drifting you towards the origin, which is your global saddle point, or are you going to move away from the origin? Right. So in order to understand that, let's look at the magnitude of my points. Let's say here I have this magnitude, and here I have another magnitude. Let's see if it is getting closer to the origin or it is getting further away from the origin. All right, so let's do that. I can compute the magnitudes from these equations. Right, so the first one would be xt plus 1 squared would be xt squared plus eta squared yt squared minus 2 eta xt times yt. In fact, I'm writing it for a high dimensional case, but obviously it's true for the one dimensional case as well. And from the second equation, from this equation, I'll have, let's say yt plus 1 squared would be yt squared plus eta squared xt squared plus 2 times eta xt times yt. Right? Now this length is basically xt squared plus yt squared. Right? So I'm going to sum them up. Sum these two up. So you see this term and this term goes away because one is positive, one is negative. So I'm going to end up with this. Xt plus 1 squared plus yt plus 1 squared is going to be equal to what? Okay, so look at this term and this term. So I have 1 plus eta squared xt squared. And look at these two terms. I have 1 plus eta squared yt squared. So altogether, I have 1 plus eta squared xt squared plus yt squared. Right? So this is basically L1 here. This is the length of this segment, and this is L2 after one update. So from this equation, am I getting closer to the origin or am I drifting away? I'm getting further and further away from the origin. So in fact, if you draw the dynamics, you can like easily do it in Python or whatever. You'll get a trajectory like this. And let's say you start from here, you're getting away and away. All right, here you see eta is actually important, right? In terms of like the rate of the divergence here. If your eta is really, really small, if eta is like almost zero in like a gradient flow type analysis, then you're gonna remain in a cycle, right? Asymptotically, because you are not getting closer, but you know, because eta is asymptotically zero, you are not, you know, getting, you know, anywhere. But even in that case, you stuck in a limit cycle, so it doesn't converge. But your eta is, if it is positive, then with a rate of 1 plus eta squared, you're drifting away from your the origin, which is the saddle point for this optimization. So as you can see, min-max is very, very different than just a minimization problem. But this is one of the simplest examples for the min-max, that your objective is just a bilinear objective. So it is linear in X and also linear in Y. And as you can see, dynamics coming from GDA doesn't actually converge. It can diverge to infinity, or from a gradient flow point of view, it may stuck in a limit cycle. Yes, eta is always positive here. Okay.
Professor?
Yes?
I'm just asking that is the same case hold for if eta is negative also, because we are taking eta square. So does we have to hold the assumption that eta is always positive, because it is the same, right?
If eta is negative, eta is a learning rate. So from the gradient, you know, from the GDA dynamics, it can't be negative, right? Unless you change your min max to max min, you can do the same analysis, and you can show that it actually doesn't converge in that case either. But from GDA, I think I should have been more explicit. In the dynamics, we know eta is always non-negative. Otherwise, it doesn't make sense to look at the minus eta times the gradient for minimizing X.
Oh, okay, thank you.
Sure. Okay. Any other questions? All right. So as you can see, this problem can be quite challenging. So there's a question, so the simultaneous gradient descent never converges? No, not necessarily. So in fact, for this example, we show it doesn't converge. But question is that when it converges, and how can we understand the convergence or some other properties of the solutions that we will find using GDA. Right, so in order to do that, let's start with some basic classical results in the min-max, focusing on the convex-concave case first. Right, that's probably a good way to start. So that's called convex-concave min-max. By convex, I mean f, my objective function that I'm minimizing over x, that's convex in x and concave in y. So there is a classical result. It's called the min-max theorem. Probably most of you have heard about it. The famous min-max theorem by the great von Neumann. 1928, it states that, all right, so here we are considering the feasible set X and Y to be compact and convex sets. It's a bounded, let's say, convex set. You see already this example that I mentioned here, it doesn't follow, because here my feasible set is the entire R squared, so it is not bounded. If the feasible sets are convex and compact, moreover, if my objective function is continuous and convex concave, so first of all, so there are several results that we can say in this setup. Okay, so the first result is probably the most famous one, that we can switch between min and max. So min over x, max over y is the same as max over y, min over x. I think this was one of the questions earlier. Okay, another consequence of this result is that, in fact, the solution is unique, kind of unique. So min max optimal point is unique. Okay, unique if f is strictly convex concave. If you look at the Hessian of f with respect to x, it doesn't have 0 eigenvalues, and same for y, and it is convex in x, concave in y. Otherwise, it will have a set of solutions. Those sets of solutions will be a convex set. Otherwise, a convex set of solutions exists. But this is the solution, x star y star. If you are in a strict convex concave setting, it is unique. Otherwise, the set of x star y star forms a convex set, but nevertheless, the value is unique. Value is always unique. This is the value f x star y star. So even if you are not strictly convex concave, you get like multiple x star y stars, all of them will lead to the same value of the function. All right, so that's the famous, very important min-max theorem. But I want to immediately note that if any of these conditions break, let's say if you are not convex concave, is non-convex concave, so it doesn't hold. So there are some easy examples that you can come up with, that you can show. In fact, you cannot switch between min and max, or you know, you will not get unique solutions either. Okay. So let's look at some additional results in this case. So this is a very classical result. You see it's 1928. So a lot of people, they studied the min-max problem, let's say, for example, for the bilinear case. So the example that we started with x times y was the perhaps the simplest bilinear case, but it was unconstrained. So if we consider a bilinear case, let's say x transpose A times y plus B transpose x plus C transpose y, it's bilinear, linear in x, everything else is constant for that, linear in y, everything else is constant for that. But here, assuming my feasible set, it is convex polytopes, convex bounded polytopes. In that case, again, we have a result, very classical result by Van Neumann and Danzig from 1947, that they showed that there is a very strong connection between the min-max theorem and the strong LP duality. Right, so I think we talked briefly last time about the duality of LP. So we have a strong duality in LP. So if you have a primal LP, you write a dual version of it, so you don't have any duality gap. So they showed, in fact, there's a strong connection between the min-max theorem and the strong dual LP. And in fact, this min-max optimization in this bilinear case can be formulated and solved using dual of an LP program. So that's an important result in this context. Okay, so what about simultaneous gradient descent that we started discussing about? So there is a result by Frond and Schapper, 1999, that they show convergence of simultaneous gradient descent and ascent in an average sense. So this is very important. Under the same setup as the min-max theorem, if f is convex in X, concave in Y, and my feasible set S is convex, compact, and bounded, right? So it's a nice feasible set. Compact means bounded, but let me make it a little bit explicit. So in that case, if your learning rate, eta, let's say set to be 1 over square root of t, t is the number of steps that you are taking, your simultaneous gradient descent, then they showed that, in fact, simultaneous gradient descent ascent converges to x star y star in the following sense. If you look at all of the values that you compute along your dynamics and take the average, say over t, tau, let's say from 1 to t, you look at the average values of x along your trajectories, and you look at the average value of y along your trajectory. So in an average sense, this guy converges to x star, y star. And in fact, the error, the difference between them, is in the order of 1 over square root of t, the number of steps that you are taking. Okay, so do we actually need this average sense, right? It's a little bit of a weird notation, right? So you have, let's say, theta 0, theta 1, theta 2, and then you are taking the average of all of these points, and then you argue that in the average sense, your function f converges to your f theta star. So in fact, as far as I know, no guarantees in this setup exist for the last iter sense. Guarantees exist for the last iter. By last iter, I mean like if you look at x and y at the last iteration and argue convergence to x star y star. So we don't have any guarantees even in this quite well-defined case. Okay, so let me pause. So this is kind of like there are so many other papers in this area. So I just highlighted probably the most important ones, obviously starting from the classical min-max theorem, and then looking at the bilinear case and looking at the convergence of GDA, simultaneous GDA in an average sense. But there are many other, interesting results in this area as well. Okay, are there any questions so far? What is S and T? So S is my feasible set. I think I defined it somewhere. Okay, so what happened? S is my feasible set, and T is the number of steps that I'm taking to basically look at the dynamics of my simultaneous GDA. These are the number of steps I'm taking. Okay, so let me move on. All right, so we talked about GDA, simultaneous GDA. Let me introduce another variant of GDA. It's called optimistic GDA. GDA or OGDA. Okay, so let's step back. In gradient descent, we know about the momentum method, right? So momentum method, if you have a gradient, you don't completely follow the gradient. Maybe you use your previous step to have a momentum, because if your gradient changes suddenly, so you don't want to follow your gradient at that point. You may want to follow a combination of your past gradient and your current gradient. You get something, get somewhere else. And in many cases, it helps the convergence of and stability of gradient descent. So this is called the momentum method. It's a very simple change in the gradient descent. So you can basically have gradient descent with negative momentum. Okay, so in the gradient descent, it's just a single minimization. It's just a history. So in gradient descent, you have xt plus 1 is equal to xt minus eta times gradient of your function at xt. But you are going to use a little bit of your past gradient to correct your current gradient. So you're going to basically undo some of your gradient at this point using your gradient in the previous step. So you are not using the the entire eta. You're using half of eta from your past gradient to cancel out your current gradient. And obviously, if the two gradients are in the same direction, the same vectors, then it basically means your learning rate is becoming half of your previous learning rate. But if your gradients are different, it means that you have some momentum from your past gradient into your current update, not to suddenly jump around. So you have some more smooth and stable behavior in the convergence of your gradient descent. So this was introduced, I think, in 1980 by Popov in 1980, which basically says use some of your past gradients to undo today's gradient. And it helps the convergence stability of gradient descent. It's a good method. It helps gradient descent to converge better and faster. All right, so what about GDA? It can be used the same idea in the min-max case to see if it will help us or not. All right, so that basically leads us to optimistic gradient descent, ascent, OGDA dynamics. In the OGDA dynamics, it is very similar to the gradient descent with negative momentum for each set of max and min variables. Within OGDA, we have xt plus 1. Before we had xt minus eta times gradient of xt yt, right? So this is my previous update for gradient descent. But now I'm going to add a little bit of my past gradient to undo my gradient at this time. This gradient is computed in a point xt minus 1 and yt minus 1. All right, same for y. So yt plus 1 is equal to yt plus eta times gradient with respect to y, xt yt. Now I'm going to undo this plus gradient by subtracting eta over half of my gradient at the previous step, yt minus 1 and xt minus 1. And that's it. That's called optimistic gradient descent ascent. Okay, so let me pause and see if there are questions. Okay, so I'm happy you guys are answering each other's questions. That's good. Saves us some time. Okay, so let's go back to the example that we started with. The example was the case of having a bilinear objective function, x times y. All right, we know in the GDA update, we had xt plus 1 is equal to xt minus eta times yt. Yt plus 1 is equal to yt plus eta times xt. But what about optimistic gradient descent ascent? So you can just write the updates from the above equations. So xt plus 1 would be xt minus eta times yt plus eta over half times yt minus 1. And yt plus 1 would be yt plus eta times xt minus eta over half xt minus 1. So that's basically replacing the gradients with their values. So if you plot the dynamics of gradient descent versus optimistic gradient descent, so remember in gradient descent we had this case, right? So we diverge. That's the dynamics of gradient, simultaneous gradient descent ascent. So in the optimistic case, by just adding these negative momentums, in fact, we are going to converge to the global saddle point. This is the optimistic gradient descent ascent. So this very simple change really helps us to converge. And why is that? So you can actually look at the analysis of the updates for each iteration. So the reason that we are diverging in GDA, because my gradient is somehow pushing me away from my global saddle point, and after each update I get worse and worse. Right? But in optimistic gradient descent ascent, I'm using some of my past gradient, so that past gradient actually pulling me towards the origin. So the combination of these two forces, one force that takes me away from the origin, and the other force kind of pulls me towards the origin. In the combination, I'm going to get closer and closer to the origin, so it basically converges to the global saddle point in that case. All right, so that's basically a very small change, but very big help in terms of the convergence. But is it true for other bilinear functions? So we know that GDA doesn't converge in general, even for a bilinear function in an unconstrained case. But what about OGDA? In fact, the answer is yes, not only for x times y, for more general cases, OGDA converges, and that's a result recently proved by a couple of papers. You can look at the references here. Maybe missing some other references, but these are roughly speaking at the same time, proving the same thing. So it says OGDA, optimistic gradient descent ascent, has last iter convergence. Remember, in GDA, we didn't have a last iter convergence, and linear rates for unconstrained bilinear min-max in the form of transpose A times Y plus B transpose X plus C transpose Y. I think there are some conditions on A matrix here to be well conditioned to have this result. Right, so here it's good because it is not in an average sense, right? So it is the last iter convergence. So it in fact the trajectory is that it converges to my global saddle. Okay, but convergence of GDA in general, or OGDA, in a constraint case, the last iter convergence is still an open problem. So even in this very simple case of a bilinear, the results are quite recent. And in a more general case of constraint convex concave, the convergence in terms of the last iter is still unknown. So it's a good, very good fundamental question to think about. All right, but now you can say, okay, so even in the convex concave case, or understanding is limited. What about if we go to applications that we discussed, like GANs or adversarial robustness? And in those cases, we have non-convex concave. So this non applies to both of them, non-convex, non-concave, min-max optimization. What about those cases? So it's gonna be more complicated than just a convex concave case. Okay, so let me pause and see if there are any questions. Is this independent of the choice of eta? Okay, so yeah, I think there are some conditions that eta should be sufficiently small. You should look at the theorem in these papers to look at the exact condition, but there's always a condition on eta. Otherwise, you know, we don't even have the convergence in the just the convex minimization case. Okay, so it's really great that you guys are answering each other's questions. If I'm missing something, you can maybe ask at the end of the lecture. So we have about 15 minutes. So let me start talking about the non-convex concave case, right? So because that's an important point. So the first question is, what is the goal here? So in the non-convex concave case. So here we may actually be interested in finding local min-max solutions or local saddle points. So what is the definition of a local min-max or a local saddle point? So here I'm going to call X star and Y star a local min-max. Again, if I fix Y star, my X star should be locally minimizer of this function. And if I fix my X star, my Y star should be locally maximizing this function. So before I wanted these two inequalities to happen globally, but if this happens for X and Y in a neighborhood of my point, X star and Y star, let me call it this neighborhood, let's say a ball, maybe with a radius of delta near X star and Y star, then I'm going to call X star and Y star my local saddle point. So it may not happen globally, but in a local neighborhood. So let's say if I have X star and Y star in a local neighborhood, X star is the minimizer of my function, and Y star is the maximizer of my function in this local neighborhood. So if you look at globally, it may not actually be the case. Okay, so in this case, we are also interested in stability of these questions, of these solutions. Right? So what do you mean by stability? Okay, I may not be able to find global saddle point. I may end up in a point, let's say X star and Y star, and this point may be a local min-max, but if I'm a little bit, away from this point, if I'm basically starting from a point very close to X star and Y star, I hope my dynamics take me to X star and Y star, or at least I hope that I don't go away from X star and Y star. Let's say I start from here. So if I then drift away, go somewhere else, then it is not stable, right? So this dynamic around X star and Y star is not stable, unstable, or unstable. On the other hand, if I start close to point X star and Y star, and I remain close, right? So I always remain, I may not converge to X star and Y star, but I remain close. So this is called asymptotically stable. I don't converge, but I don't, drift away from X star and Y star. But if it happens that my dynamics, in fact, takes me to X star and Y star. So I have X star and Y star. So I start somewhere nearby, but my dynamics takes me to X star and Y star. It's called locally asymptotically stable, or it is attractive. Attraction, in fact. point. So this attracts the dynamics to converge to X star and Y star. So these are three kind of concepts that we care, right? So asymptotic stability, if dynamics starts close enough to theta star, then it remains close. So that's one definition. But if dynamics in fact converges to theta star, we say it is locally asymptotically stable, or this point is an attraction. So that's stability that we care about. So in fact, we want to find these, even if we find these local saddle points, we want them to be stable. We don't want to say if you're, epsilon away from it, then your dynamics are going to take you away. Okay, so let me see if there are, is there a bound on the radius of the belt? Yes, all of them, there are some bounds. All of these definitions, in a way, I'm, having them in a hand wavy fashion, just to give you the intuition, but there are epsilons and deltas involved in all of these definitions. Amir, go ahead.
So in the regular ERM learning setting, it's sort of intuitive that like having a global min is good and your neural network is performing better, in quotes. But in the GAN objective or the min-max objective, is it even obvious or intuitive that the global saddle point is better or the best place? Like, does it generate higher quality data, or is that not the case?
Good question. But at the end of the day, I want my X player to get the minimum of that objective function, and my Y player to get the maximum of that objective function. And if that holds globally, that should be better, unless your objective function is not properly designed. So from that point of view, if the objective is designed properly, getting a global saddle point should be better than getting a local saddle point. Having said that, sometimes there are some empirical evidences or some heuristic evidences that they argue that some local saddle points may have some other better properties in terms of generalization and some other behavior in terms of like the quality of like say samples generated from the model. But those are I don't think those are very rigorous, and at the end of the day, here we have a min-max problem. My goal is to find a global saddle point, but if I can't find it, I'll settle to a good local saddle point. But at least I want my local saddle point to be stable, so I don't want to drift away. If I start from a point very close to that point, I don't want to drift away from that point.
Makes sense. Thank you.
Sure. Okay, so let me see how much time I have. I have about 5 minutes. Okay, so let's go back to the GDA dynamics that we started with. So in the GDA dynamics, we have theta t plus 1 is equal to that function f applied to theta t. And that function was basically theta t plus eta times my gradient vector. And if you recall, the gradient vector is one component is a negative gradient with respect to x, and the other component is the positive gradient with respect to y. Okay. So it is important in terms of the convergence of the dynamics, in terms of the ability to find the fixed point, to look at the Jacobian of function f. of function f, which is basically the gradient, the derivative with respect to theta. And the Jacobian can be, the derivative of the first part is basically the identity function plus eta, which is a constant. The derivative of my gradient would be the Hessian matrix. And that Hessian matrix is basically defined as the following. So here, I basically look at the gradient of this vector, the gradient vector with respect to x and y. So I'll have like the double gradient with respect to x. Here, I have the gradient with respect to x and y. Here, I'll have the positive gradient with respect to x and y. And here, then the gradient of this guy with respect to y would be double gradient with respect to y. Okay, so this is the Hessian matrix that I have here. So one other definition of stability relates to the eigenvalues of this Jacobian. So if the eigenvalues of the Jacobian is bounded by 1, if it is larger than 1, it means there's a direction that your energy increases, so you can diverge. So you may not end up in a fixed point. But if the eigenvalues of your Jacobian is bounded by 1, it means that it is a contraction. So you'll basically converge to a fixed point. So that's the definition of what it's called linear stability. So it says a fixed point, theta star, is stable or linearly stable if I look at the spectral norm of my Jacobian evaluated at theta star. So this is equal to magnitude, largest magnitude of eigenvalues of my Jacobian. So if this is less or equal to 1, then I'm linearly stable. So I'm not gonna drift away from my point. But here we have the equality as well, right? So it may be possible that I have an eigenvalue to be equal to 1. In that case, that eigenvector is not going to shrink the energy of that eigenvector when I'm applying this function, multiple times. So there's a kind of a trivial lemma that if you are linearly stable, but if your spectral radius is strictly less than 1, if you are linearly stable, but your spectral radius is strictly less than 1, then it immediately corresponds to the asymptotic stability. Right, so you will basically get an asymptotic stability for free. Okay. All right, I think I am out of time, and we still have quite a bit to cover, especially in the non-convex concave case. Okay, so probably I think the best is that I'll pause here and take questions, and in the next lecture we'll continue talking about non-convex concave min-max optimization problems.